Hello, my name is Matthew and I have the privilege of being paid by Ericsson to make the world a better place through open source, and for that I am grateful. This is a video I wanted to make for a while. It takes a step back from individual analyses and looks at the big picture. What is a bottleneck? Performance bottlenecks are like traffic jams on your computer. They occur when one part of the system slows down the rest, hindering overall performance. Now, I want to be clear. A system will always bottleneck. Why is that? It's because a system can never be perfectly balanced or tuned. Also, it's okay to bottleneck, as long as you understand what's happening. Let's look at some simple transactions using Trace Compass. In this tool, we offer a critical path view. The critical path shows, by its design, only the bottleneck. Full stop. When your code executes, it can be seen as a collection of flows and sync-up points. The critical path analysis shows one flow that's holding everything up. Now, I'm going to give an example using apt. This is apt, the wonderful package installer for Debian-based systems. We have a trace where we install tree. Now, tree is a program that requires under 100 kilobytes of data. It takes 4 seconds to install. From here to here, 4 seconds. Now, assuming your hard disk can write at 100 megabytes a second, we're spending time doing other things. This is a classic bottleneck. But if you spent all your time waiting for the write, it would still be a bottleneck, but it's the expected bottleneck. Now, if we go to the critical path view, we can see the interesting observations. The first 600 milliseconds are spent on the computer side. It's probably doing setup and whatnot. And then I'm going to open the legend. We have a network delay here. And then after the network, please remember, timer, and block device is purple. It's right here. We have the 150 milliseconds around. Let's see, 150 milliseconds-ish, where we download the packages to memory. And finally, here our program yields because it's being preempted by other programs. You could see that it's dpkg, which is part of the package management, so this is fine. And then we spend a lot of time in a timer, followed by here certain disk I/O access, and in the end, apt checks. If we look at this in an aggregate form, it becomes even more interesting. Like this, I will bring it up here. You could see that most of your time is spent waiting for other processes to run, and you're spending 1 second running, and you're spending 1 second waiting for the timer. If you look by process name, you could see that most of your time is spent on your own program, but that apt check is doing a lot of stuff, and that's actually really good. You want to be able to verify that things are not broken when you install a new package. So, let's say you have something a little less complicated, and I'm not throwing any shade. I want an architecturally simpler program, and I'm talking about a video game. So, this is an example of a video game that was done in the bad old days. The CPU will do work, and then it's going to wait for the GPU, and then it's going to display the frame. And they'll do more work, and they take turns. So in this case, your program is going to be bottlenecked by both the CPU and the GPU. Why? Because it spends half of its time waiting for one, half of its time waiting for the other. Now, let's go to a slightly more modern system. Let's say this one would have a multi-thread access, but it would still be the same. Here. This is a pipeline. So you have frame 1 that's being prepared and rendered. And when frame 1 is being rendered, frame 2 is being prepared. So your CPU and GPU are working in parallel. And this is a perfectly balanced system. At this point, it is balanced, but there will be... This is the ideal, but it will never happen in reality. Let's take a look at some other examples where, let's say you have a strong CPU at first. So now you're preparing your frame, and you're rendering the frame. And you can only start preparing the next frame once you get your input. So at this point, you see that your CPU is active for a certain amount of time, and then it's inactive. If I do this and I highlight over, I can see that the CPU is active for 60% of the time. This leads to an interesting point. People will look at their CPU utilization, and they'll say that their CPU is 60% utilized, or their GPU is 60% utilized. This is an aggregation. Your CPU is either working or it's not. Your GPU is either working or it's not. When you see 60%, it means that over that time period, it spent 60% of its time working. Now, let's say that, on the other hand, you have a stronger GPU. You could see here, your CPU is going to be spending a lot of time preparing the frame, and your GPU is going to be spending very little time preparing the frame. So if you take, for example, this frame here, and you look at your CPU usage, it's around 100%. You could see it 99%. Your GPU is about 40%. And this is what's happening. However, here's where reality sits in. In the real world, you'll have your GPU and your CPU that have a certain amount of overlap. But there's going to be a certain amount of time where the CPU is waiting on the GPU or vice versa. There can be many reasons for this to happen. For example, your driver that's putting data from the CPU to the GPU. And because of that, you are never truly bottlenecked. You're always going to have certain critical sections on one, certain critical sections on the other, and you'll always get a certain performance boost from one side or another. So what takeaways can we have? All that we've shown can explain why increasing the performance on one of the two elements will increase the total system performance. When dealing with bottlenecks, one should be restricted to a single flow, or in this case, a single frame. This is, again, since workload changes from one frame to another, will change the balance, and therefore the bottleneck, or the critical path, will change from one flow to another. I sincerely hope this helps understanding bottlenecks in general. If you have any further questions, don't hesitate to leave them in the comments. Thank you.